So we can, all these hours today would be, it's okay, right? So let's do more induction, some simple and hard problems. I'll talk a little bit about the induction to binary search tree, and I'll take that chance to recap a little bit binary search tree. By the way, that's due when? Others problem, what is it, 4? Due Friday, 11:15. So let me, I actually don't know if we did this one or not. Did we do this last time? If I say S of n is S, I think this is S2 of n. 1 squared plus 2 squared plus 3 squared plus n squared. That is sum for all k equal 1 to n of k squared. And the statement is that this sum is n times n plus 1 times 2n plus 1 divided by 6. Did we prove this? I know I stated on the board. Did we do the proof of this thing? This class? Right. So the induction step, well, we'll just do it because we're here now. This is n to n plus 1. So that's a weak induction step. It's saying if this sum is n times n plus 1 times 2n plus 1 divided by 6 for n, goes from 1 to n, then the same sum to n plus 1 goes to, now who's that? That's n plus 1 times n plus 2 times, this is 2 times n plus 1 plus 1 by 6. So it's saying if this property is true for some n, like n equals 95, then it's going to be true for 96. And the proof of this induction step, this will do just a sketch, because I think it's easy to follow. It's always relating the new troublemaker here with the previous troublemaker. Says, what do I have to do? I have to do this sum. How does that relate to the sum for n? So how does this relate? This sum all the way to n plus 1 of k squared is, of course, the previous sum, plus the next term, n plus 1 squared. So now, the reason this is very useful in induction step is the previous sum I already know. It's an induction hypothesis. What it is, I can put it here, n times n plus 1 plus 2n plus 1. This sometimes is very easy and nice to write here. That's an induction hypothesis. The reason I can replace this with that is the induction hypothesis, plus the new terms, n plus 1 squared, right? That's the additional term that I added to go to n plus 1. And now comes the algebra, the manipulation step, to say, okay, this is what I am, and this is what I'm trying to get. So that comes, okay, how do I make it nice from here to there? And I'm looking at 6 is 6. That would be nice to keep in the front, because I'm going to need it anyway, right? And I see an n plus 1 that's needed, so let's keep that in here, with n plus 1 by 6. And then I see what's left of here. Well, I got the n plus 1 and the 6, so this is n times 2n plus 1 left from here. Now what's left from this? I got an n plus 1 in the front, so I still have an n plus 1 because this is a square. But I have 6 of those because I forced a 6 common factor, which was not there. I have to put it back. And now I'm going to leave this as an exercise for you guys. Now, this n plus 1 by 6, I already have the n plus 1 by 6, kind of I don't have to worry about that one. I'll have to prove that this inside here is the remaining n plus 2 times 2n plus 1 plus 1. That has to be equal to this one. It's just a simple manipulation. So then I have a base case, of course, n equal 1. It's manual check. We don't have to worry about, when you do base cases, just check them manually, plug in n equal 1 and see what happens. So the way to see this is to look at the chain of implications you already proven. After the induction step, you have something like P of 1 implies P of 2, implies P of 3, implies P of 4, and so on and so forth. This chain never ends. To make all of them true, now that I have the implication proven, doesn't mean they are true unless the first one is true. So that makes my base case. And we've done some problems where you have multiple chains or multiple interleaving chains. Everything that's not the end of an arrow needs to be proven manually as a base case, because that doesn't come out of the implication induction step. Here's another one. So that's the first one for today. I have this sequence that says S1 is 1, S2 is 3, and then for any k starting at 3, because I already have the first two. This is a recurrent sequence. It's defined in terms of itself. Induction works really well on recurrent stuff because induction step, it's a way to relate the new customer with the old customer. So it makes it, it's an analogy of recurrences. So this Sk is defined as Sk minus 2 plus 2 Sk minus 1. So just to instantiate how this works, who will be S3 then? According to this formula, it will be S1 plus 2 S2, right? That will be S1 is 1 plus 2 times 3, that's 7, right? Who will be S4? S2 plus, I'm applying this formula for this is k equal 3, k equal 4. S4 is 2S3. How much would this be? S2 is 3 plus 2 times 7. How much is this? 17. How about S5? That's S3 plus 2S4. That is S3 is 7 plus 2 times 17. How much is this? 41. So you can see how from the base, I have a base. This is the base. The recurrent formula allows me to compute all this sequence, right? All these numbers. And now let's make a statement here. P of k, the one we want to prove, is Sk is always is odd. This is from the regular section because it's obvious, right? It's odd. I mean, let's do a proof quickly. What is it? Why is it odd? Let's do it by induction to serve the purpose of the objection, right? So what kind of induction do I need? I'm going to prove by induction. So what's the induction step? Actually, this is a very good example. It's super trivial to prove. Of course, all these guys are going to be odd. Easy to see. But when you write the induction step, the best induction step that you can possibly write is exactly who implies who. Don't just say strong induction, weak induction, structural induction, da-da-da. Just say exactly who implies who. So in this case, I want to get P of k imply who I'm gonna need to get the statement for k. I'm gonna need P of k minus 1 and P of k minus 2. I'm gonna need those two. Now, if you want to write what kind of induction is this, is it weak or strong or structural? What is it? This is a strong induction because it's not just k implies the next one. K minus 1 implies k. You need more than just the previous one. Actually, we just need 2 in here, but nevertheless, because we need the previous 2, that's a strong induction. So it's nice to write, especially in an exam, exactly which statement from before are you going to use to prove that. So how do we prove this? Like to prove it's trivial, right? the reason we need those is look at the recurrence, right? The kth value, kth item in the sequence, depends on the previous two. That's why we're going to use this induction step. Every time we got a recurrence, something that depends on itself, exactly what before it depends on will dictate how the induction works. If this would depend on sk minus 3, sk minus 3 would be here. If this would depend on sk by 2, sk by 2 would be here. Because recurrence, we'll have to use the previous, whatever we proved for those previous values. So P of k, S of k, sk is sk minus 2 plus 2 sk minus 1. Now this is, by induction hypothesis, this is odd, and this is odd, right? Because what I'm trying to prove is this is odd numbers. Since I got to k, I already proved this is odd and odd, right? So this is now an odd plus an even. I'm going to skip some steps here. 2 times this is even. Can I say this is odd directly? Is that okay? Say an odd plus an even, it's always an odd. I mean, if you're not sure, you can try to prove those things. I think this is elementary enough to just state it that way. If we were to really do it, this is 2p, and this is 2q plus 1. The whole thing is 2 times p plus q plus 1, so that is a odd number. P and q here are generic. Okay, so that is easy. And then I can do a base case. Try k equal 1, 2, and 3, verify sk is odd. I can do those manually. I can just look at 1, 3, 7, 17, they're all, so that's good. Now, I use the fact that pk minus 1 and pk states sk minus 1 is odd and sk minus 2 is odd. This is the induction hypothesis. Could I have done this only with sk minus 2? Could I have done the induction step? Pk minus 2 implies pk. Could I have proven this only knowing sk minus 2 is odd, not sk minus 1? Of course I know that because I prove all of them are odd. But if I wanted an induction step like that, could I have done this in this problem? If I look at this, can I say, you don't need to know sk minus 1 is odd. Just the fact that this is odd plus 2 times that one, which could be anything, it results in an odd number. I think that would work. How about pk minus 1 implies pk, weak induction? Could I just use the fact that sk minus 1 is odd without knowing anything about sk minus 2? Could I have said now, because this is some number plus 2 times an odd, is that an odd? Would that work? No. This doesn't work. That would still be strong induction, even though it's just 1 implies the 1, k minus 2 implies k. It's still a strong induction because it's not from n to n plus 1. All right, here's another one. Write another board here somewhere. It's very similar. S0 equals 0, S1 equals 4, and Sk is 6k minus 1 minus 5sk minus 2. That's a very similar kind of equation. It's a recursive sequence. It defines any new value in terms of the previous values. It so happens it's also the previous 2 values. So it doesn't go too far to see what values I need. And here the task is, who is Sk? When I say who in a recurrence, this is still a recurrence, sequence. I'm asking, I want a non-recursive form of SK. I could have asked the same one in here. Here's an exercise. Let's put 3 stars to it. Who is SK? As in not recursively. Can you give me SK as a function of K? Like K squared plus 3K plus log of K plus 5. Something like that. Not recursive given previous values. Maybe somebody can do that. I'm not asking asymptotically. That's an easier question, just 1 star. Who's SK as theta of a function of n? Say, you know, that's like n squared asymptotically. It's not exactly n squared, but it's kind of like n squared. That would be an easier question. This asks exact. Can I get a closed form expression for SK? Let's do it here. There's no stars here, right? Well, let's kind of work it out first. Maybe we can, the way to do this problem is to first try it out. Maybe you get an idea. So S0 is 0, S1, who's the next one? S2. So this is trials. Let's see, who S2 is? It's 6 times, who's the previous one? S1 minus 5 times S0. So that is 6 times 4, 24. How about S3? That's 6S2 minus 5S1. That will be 6 times 24, right? Minus 5 times, who's S1? 5 times 4, how much is this? All right. Who's S4? 6 times S3 minus 5 times S2, so that is 6 times 124 minus 5 times S2. Who's S2? 24? Is that right? How much is this?
600.
How much?
Wait, never mind.
Can anybody do this calculation for me?
It's 624.
624. Okay? Now we're looking at those values as a sequence. 0, 4, 24, 124, 624. Anybody can take a guess? It really comes down to a guess in here. Of course, it's an educated guess. Mathematicians have a better chance of guessing than non-mathematicians.
5 to the k minus 1.
5 to the k minus 1. Is that simple guessing, right? Like looking at those values, this looks like 5 to the 0 minus 1, 5 to the 2, 5 to the 1, that's 5 minus 1, 5 to the 2 minus 1, 5 to the 3 minus 1, 5 to the 4, that's 625 minus 1. So his guess is like, I'm not sure, but like let's put that in. Let's see what happens. Now guesses are very good because we can immediately verify if this is correct. My induction should work out quite easily. So what's my induction step here? This is my hypothesis that this is SK, this is my P of K, right? My statement. SK is that value. It's a guess for now. Induction step will be, what P's do I need to prove the PK? I do PK minus 1. Is that enough? No, because the recurrence will dictate that I need to know something about this one and something about this one. That's how this recurrence works. It depends on the previous 2 terms. So I'm going to use the previous 2 statements. That is, I'm going to say SK minus 1 is 5 to the K minus 1 minus 1, and SK minus 2 is 5 to the K minus 2 minus 1. Then try to do this one. Okay? Proof. I always start with a new customer. That is, I'm going to rewrite this induction step to be more clear. If SK minus 1 is 5 to the K minus 1 minus 1, and SK minus 2 is 5 to the K minus 2 minus 1, then I want to prove SK is 5 to the K minus 1. That's that written in explicit terms, right? So my proof is always start with SK. How does SK relate to the previous ones? In recurrences, that's just the recurrence. That's how it relates. Use the recurrence. So it's 6 SK minus 1 minus 5 SK minus 2. Now I use the induction hypothesis here. Now who's this? It's 6 times 5 to the k minus 1 minus 1 minus 5 times, who's SK minus 2? 5 to k minus 2 minus 1, right? Now the algebra comes into play. We have to manipulate this to get 5 to the k minus 1. So let's see. I think it'd be very useful to think of this 6 as 5 plus 1 rather than a 6, right? So if I say 5 plus 1 times 5 k minus 1 minus 1 minus, I can open this parenthesis here. 5 times 5 to the k minus 2 is 5 to the k minus 1 minus 5 times minus 1, that is plus 5, right? So now let's see how this works. 5 times 5 to the k minus 1, that's 5 to the k. 5 minus times minus 1, that's minus 5. 1 times this is plus 5 to the k minus 1. 1 times minus 1, that's minus 1. Minus 5 to the k minus 1 plus 5. Let's see who goes away here. This one with this one. The 5 with the 5. And this is 5 to the k minus 1, which is what I want. Induction is not that hard in most cases, especially at this level when you just saw it. The problems you're going to see in the homework and exams are not hard induction questions if you know where you're going. The real difficulty in this kind of problem, if you don't know, it's 5k minus 1. Trying to guess it could take a long time. And sometimes induction doesn't help guessing. Like you try a value that's not this. You kind of try 5k minus 3 to the k, or minus 2, or minus some polynomial. The reason it doesn't work, it's because it's wrong, of course, but it's not helpful in guessing the second time right. You would like to have, ideally, some sort of systematic way of saying, if my guess was wrong and it doesn't work, can you at least point me to the right guess somehow? And that's sometimes the difficulty with induction problems. I think this is a better way of guessing. Literally, just keep going with this thing. And if the numbers get too hard, use MATLAB to plot it. That's a better way of guessing it than trying induction proof, it doesn't work, change the guess, it doesn't work, change the guess, it doesn't work. I think this, just see how the function evolves, it's a better systematic way. There are other better ways, but it requires more complicated math. Okay, so we've done that one. Very good. Let's do the, I think we've done one problem last time in class. Well, I'd like to get back to it because I think it was rushed up. I want to make sure everybody understood that problem. And we'll make an add-on to it. So the problem was with n lines in 2D plane. They are not parallel and not concurrent. They don't pass to the same point more than 2, and they're not parallel. So I have something like this. And the question is, how many regions? How many visual regions? Like convex regions. And in this case, the regions we have where, what is it? 1, 2, 3, 4, 5, 6, 7, right? And we have a hypothesis. The number of regions, I think that was given, is you guys remember what n squared plus n plus 2 divided by 2. I know we've done the problem, I want to recap the setup, and you have to deal with base cases. I just want to make sure everybody understands how that problem works. This is more like a structural induction. So what really we're going to do induction over n. So that refers to the who is the variable that's being inducted by. Sometimes we have k, x, and n, and when you specify induction, you want to say induction over k or over n. That means I'm going from n to the next n, not to be confused with k or the other variables. Induction over n means our new customer here. So the induction step is going to be if n lines produce n squared plus n plus 2 by 2 regions. That's my statement. Then n plus 1 lines produce, how do I write this for n plus 1? n plus 1 squared plus n plus 1 plus 2 divided by 2. Right? So that's induction step. Remember, like always, induction step is an implication. It's that if it was true for n equal 5, it's going to be true for 6. This is weak induction. Even though the problem's complicated, the step goes from n to n plus 1. So the reason I want to bring this problem, I want to make sure everybody understands the geometry of what happens. Here's the line n plus 1. I'm going to write on it n plus 1 line. So now the proof. n plus 1 line intersects the other lines, say in points x, if this was line 1, this is line 2, and this is line 3, in points, let's call them x1, x2, and x3. Right? In points x1, x2, x3, say, let's say in this order. So we're not going to pick them at random. But it's clear why there are 3 of them. This line up to xn. It has to intersect all the other lines and lines. So it'll be n intersection points. I'm reading the points in the order of line n plus 1. So now because I have these n points of intersection, I'm only looking at the intersection between this new line and the previous lines. How many intersection segments I'm going to get? I'm referring to, say, this is a segment here. This is another segment here. This is another segment, goes to, doesn't have an intersection point. That's an infinite segment, goes that way. And here's an infinite segment here, right? If I have n points, how many segments on that n plus 1 line? Because these points are on n plus 1 line. If I have n intersection points, how many segments that segments into the line? N plus 1. N plus 1 segments. That means how many of the previous regions have been split? Not all regions. Before this line, I had 7 regions in here. Not all regions got split by this line. For example, this region 1 and this region 6, they still intact. But region 3 now, it's split, right? It's 3 and 3 prime. And this region 2, is it intact or is 2 regions now? 2 and 2 prime, 4 and 4 prime, maybe, and 5 and 5 prime. So how many regions, if I have n plus 1 segments, n plus 1, each segment is in an existing region. So that means n plus 1 regions are doubled. Again, that, like in here, this region 3 is now 2 regions, 3 and 3 prime. Region 4 is 4 and 4 prime. Those are the regions that this new line passed through. So the total number of regions after n plus 1 line is how much? Is all the regions I had before n plus 1 line plus n plus 1, right? If I've got n plus 1 regions to double themselves, the additional regions is n plus 1. So now if I do the calculation, I get n squared plus n plus 2 divided by 2 plus n plus 1. And you guys, as an exercise, have to prove that this is this. Manipulate a little bit the terms to show that the existing number of regions I have plus the new ones have to be the number I'm trying to get at. That's very easy. It's just a simple manipulation there. Now, this induction proof is not different than the other induction proofs. I mean, it has geometry and lines. But the basic induction step is still relating the new customer with the previous customer. The reason induction applies so well here is that the new number of regions is clearly the old number of regions plus how many of them got split. Because if 3 regions are split, now will be 3 extra. If 5 regions got split, there will be the original 5 plus the 5 new extras. So every time something relates to the previous value, induction applies very naturally in those cases. So I think we've done this, but now I want to add a problem to it. Second problem, yes?
You said the word structural induction twice. What does that imply?
Right. It's just a very good question, and I had the same question when I started teaching this course. I never heard that before in my life, structural induction. And I'm like, what is it? Well, if you think of those P's, P of n is a statement, and I'm applying P of n plus 1, or P of, say, some previous P's implies the next P, is no difference. P is a logical statement, it's either true or false, and has to do some property or some summation or a product or a bunch of lines, whatever it is, and you try to prove that if the statement is true for previous cases, it's true for the next case. Now, structural refers to some structure of the problem that's not just a summation. Something to do with a tree, with a bunch of lines, maybe with parentheses, or something that's, you have to look at the structure of how that thing works inside. If I tell you this about trees, which we're going to do in 10 minutes, you're going to have to use the tree structure to determine how the induction progresses. In here, clearly it has to do with lines and with 2D plane. Like here's an exercise. Is this happening at 3D plane? Can you write the same exact problem, but lines becomes hyperplanes and the space 2D becomes 3D? Can you determine each new hyperplane, how many regions you're gonna add to the 3D plane? And if that's too easy, how about in a general D plane? Like, you know, the D-dimensional vectorial, how this equation plays out. Clearly, this has to do with the structure of the space, because in 3D or 4D or 5D, equation will be different. It has to do with how lines and intersections works in 5D or 7D. That's what it, but I think logically, from an implication standpoint, all inductions are the same. Relates the previous true statements piece with a new one. Even the weak versus strong distinction, it's not so you know, important to me. If you say, if you write this up, what exactly am I proving in the induction step? I'm going from the previous two to that one, or all the previous, or the half to the new one. That's exactly what you need. You don't need to know if it's strong or weak, just who implies who. Okay, so let me add a problem. I'm going to do the same exact setup. So I'm not going to redraw this, but it's a totally new problem. We want to show that if we do this thing with lines, it's always possible to color. So here's the next problem. Color regions such that every in two colors, such that every two adjacent regions have different colors. In other words, let's take this the simple case with two lines. I'm gonna call adjacent the ones that have a segment in a side, a border, not a vertex, because all four have the same vertex, but they have a side. Obviously, I can color this one black, this is white, this one here is black, dark pink, in my case, let's say it's black. You see what I mean? For two lines, it's clearly possible to color them such that every two regions that have a segment in common have different colors. How about for three lines? I mean, if I color this interior here black, I have no option, then this one has to be white because it has a segment in common. This one has to be white, this one has to be white. But not this one white, this one has to be black. This one has to be black, right? And this one has to be black. Does it make sense what I'm doing here? I'm coloring with two colors, white and black. And I don't want, like, imagine a map with countries. We don't want the countries that share a border to have the same color. People get lost with the border, right? So can I do it with two colors, no matter how many lines you have? It doesn't work for four lines. Let's try it with four. So again, what was my four here? And I drew the fourth one this way, right? So now how would I color this? If I start in the middle with something is black and white are symmetric here, so it doesn't matter how we start. If this is black, this one has to be black because it's white. This one has to be black. Now this is black, this one has to be black. This one has to be black. Right? Who else has to be black? This one here? Would it work? Do I have all the regions colored such that if there is a adjacent segment, not vertex, segment, they have different colors? For example, this and this have a segment, they have different colors. This and this have a segment, different colors, so on and so forth. It does work, right? Looks like, seems like. Can I prove this? Now, I'm sure there are, in fact, I know for sure, a geometry proof that has nothing to do with induction. If you have so many lines, here exactly how you color them, and you prove geometrically with some trigonometry that the split works. But I'm thinking of a proof by induction. What would the statement be? If I want to prove, my new problem is, no matter how many lines you draw, there is a way to color them, the regions black and white, such that any two regions with a common segment will have different colors. Hands up is with me what the problem is. Okay, any questions? I draw a bunch of lines, doesn't matter how many, 90 lines, 100 lines, 1,000 lines. I want to prove under the same setup. No two of them are parallel, no three of them are concurrent. I want to prove that there is a coloring schema such that for every region, such that the regions that have a segment border, they have different colors, like countries on a map. And I want to do this by induction. So how the induction step would look like? Yes?
You draw n+1 lines and then remove a line, which like say it can be colored, and then put that line back in and say how you continue the coloring.
Right. So the induction step, if there is a coloring schema for n lines, that satisfy the validity, right? That adjacent regions have, adjacent means they have a segment in common, have different colors. Then, that's the implication, the induction step implication. There is a coloring schema that does the same thing for n+1 lines. This is a weak induction step. Maybe weak induction is not enough. Maybe we need to know more than the previous step here. But let's try weak induction. Now, what he's proposing is a way to start. He is proposing not the full proof, but what he's saying is, how do I relate my new customer with the old customer? Who's the new customer? I have n+1 lines now. And how many regions? A lot of regions, right? Where is it? Somewhere in there? Oh, here's how many regions I have now. Right, that's the previous problem. I have n+1 lines, that many regions. So how do I relate? I'm going to draw that again. I have my lines here. And how do I relate n+1 lines situation with regions and colors with the n line situation with regions and colors?
Wait, real quick, so let's say that was an example question, right? Would I have to prove the previous problem separately, or could I use that what we proved before as a definition?
In this case, they're separate problems. One says how many regions are there. The other one doesn't ask how many regions are, just show that you can color them. Actually, this problem is completely independent of this problem. We're not going to use the fact that there are that many regions here. Just, we're going to show that it's possible to color them. But in an exam, you have to be very clear what it's given, what you know, and what you have to do. I totally agree with the fact that you have to, clearly say, can I use that result or not? If it's not clear, you should ask. But back to this problem, it doesn't matter how many regions are here. We're not going to use that result. But how do I relate this coloring schema that I'm trying to get here done with the n-line coloring schema? What should I do? How the new customer relates to the old customer? Yes?
So erase one line or ignore one line and color it.
I kind of pretend one line does not exist, right? Let's say I put it dotted like that, so I kind of don't see it unless I want to see it, right? Say that's kind of saved on the back burner, that extra line. Let's pretend for a moment it's not there, right? I think you guys had to do this with dots on a circle, right? The way you do that is the same principle. You say, oh, I have so many dots here. What if I remove 1 or 2 or 3 or some number of them? Then I'm in the case that I've been before, right? So that's how you have to think of those problems. Okay, so what's the coloring schema for 3 lines? Can I assume there is one for 3 lines? From the induction hypothesis, right? I'm assuming this was true for the previous, and in my case, I go from 4 lines to 3 lines. So the coloring schema was, okay, this guy here, this in here is black, and this in here, right? That's coloring schema. Let's be very careful how we do this here. This line means this coloring schema is going to go all the way to that line. I'm pretending for now that this new line does not exist, right? Because I do it for 3, that means I'm not looking at this line. I'm only looking at 3 lines. And I say there's got to be a coloring schema for 3 lines. Maybe this one, maybe different one. Now I'm adding that thing in, right? That new line. Now I'm saying you have all these colors, and you also have the new line. Clearly, this is not a valid schema for n+1 lines now. Why is that? Why the previous schema can I just leave it be? Is this a valid coloring schema for now 4 lines? Why not? Somebody loud, yes.
Because part of the solids are being like bisected.
And they don't satisfy anymore. They have a segment in common, right? You're talking about this segment here.
Yeah.
This clearly cuts, and the 2 regions have the same color. And this segment in here, that's another problem. Cuts a region that's white and white, and this segment in here cuts a region now that's black and black. So now it comes that creative step when I say, okay, I need to take this coloring schema and modify it to get a valid schema for n+1 lines instead. Yes. Is that a plan here?
If the segment is cut by the line, switch the color of the next, like of the segment that's created afterwards.
So I'm assuming the 3 lines are the first 3 ones, and this line number 4 is the next one. So what should I do? How do I, clearly there's a problem here. They're both white, both black, both white, and both black. Is there a way to fix this now that I get the valid coloring schema for, let her answer again if she wants to.
How
where do I start?
So like every single time a segment is cut, you switch the color of
You
that.
mean this segment
Yeah.
or this segment?
So like in the original photo segment 2.
This segment,
Yes.
the original one. Okay, this one is cut here by the new line. Yeah.
So you switch the color that was originally on either side. So like
I
black
switch
becomes white.
this one and this one,
Yeah.
but I have four regions here now. The two regions that were originally here, black and white. But now with the new lines, I now have four regions, black, black, and white, white. So which exactly do I switch? Which ones? Yes.
I think she means just like flip everything on one side of the line. Like
Of the new line or this
the
line?
new line. Just
Huh?
like change on the new line, just like change the color of each region.
So I'm gonna, you proposing, think of this side as the left side of the new line and this one as the right side.
Yeah.
And pick the right side and say everything on the right side is flip.
Yeah.
Okay? So all regions switch colors. Right?
That way each side is still fairly consistent and along the border.
So how would that work? This one was black, now it's gonna be white, right? This one was white, now it's gonna be black. This one was black, it's gonna be white now.
Yeah.
And this one was white, now it's gonna be black. Is this a valid coloring now for four lines? But can we prove? I got the mechanism, but now the mechanism is well defined. This is how it works. Pick a sign of the new line, like the right side, or if it's like the upper side, or you find a way to define one side versus the other side. One side, keep colors. The other side, flip the colors, swap them. Now we need to prove that this is a valid schema.
Clearly the left side is valid because you don't change any of the colors.
Right, this side is good because what's good from before.
Yeah, and then all the sections that touch on the line that you added are fine because they were the same color and you inverted it, so now they're all different colors.
So what he means is the ones that were the same color, white and white like this, you mean? Now,
Yeah.
one was staying left side, remaining the old color, and the one on the right side swapped, so they're different colors. How about those that were on some existing line flipped? To be valid from before, they had to have different colors across any, like those two or those two or those two, they were different before. What happened to them? Why?
They're all flipped.
They both flipped, so white became black, black became white, now they're still different, right? So now that we said the proof, you have to go home and write it formally, exactly how this works. There are the regions that were all on the left side, they stay the same. There are the regions that are on the right side, there are two kinds. The ones that were the same region and got split, and the ones that were different regions, but now both flipped. So the difficulty here, once you settle upon induction, is the creativity step. Okay, from the old colored schema for 3 lines or for k lines, I have to figure out how to change that to make it work for k plus 1 lines. That's the case of structural induction. This particular mechanism clearly will work in this case because of lines and 2D and the regions being, polygon that are convex. It wouldn't work for other things. Try to do circles, for example.
For this coloring condition, do we need that the lines are not parallel and that they're not concurrent?
Well, if you have a line parallel with this one, we'll have to think of what that happens. I think it still works.
Yeah.
Because one side of the line will be that, the other side will be all the other regions. But for simplicity, let's say, you have to control the intersection points. I think that's a little difficulty in the previous problem, where you add how many regions. If you add a line and it doesn't have that many intersection points because it's parallel with 3 other lines you had before, then you're not adding that many regions. But for coloring, I think it works fine. All right. One more induction problem. Some of you might have seen this as a puzzle. I have L shapes that they look like this. all rotations of it. Three squares. So I have infinite amount of these L shapes, and I can put them in any way I want because I can rotate them. And I have a board that is 2 to the k, k. It's full of squares, right? So let's take k equal 3 here. 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7. I got 8. So the board is 2 to the k by 2 to the k. In this case, k equals 3. And one of these, at random, one of these squares is blocked, is taken, or blocked. Pick one at random. I'm going to pick one at random, this one. The task is fill the rest of the board. So I have a board, it's 8 by 8, or 16 by 16, or 32 by 32, something like that, right? Power 2 times power 3, it's a square. And then I have as many of those shapes I want. No problem, infinite number. And I can put them in any way I want, but of course a shape has to cover exactly 3 squares. Like if I put a shape, you can't put it on a diagonal, you have to cover exactly something like this, right? Is there a way to put those L shapes to cover everything but one square which is blocked? You have no control over which square that is. That's like given by the problem. Sometimes that square could be the corner of the board, could be the middle, could be anywhere. You can't, it's a big rock, you can't move it, okay? It's there. You have to fill the rest with tiles. Can we do it? Of course we can, right? How would I say it here if we wouldn't be able to do it? Right. But this is a complicated problem if you don't know induction or if you don't think of induction. If you want to do this on a general board with those L's, ask somebody who's a scientist but not a mathematician. Hey, fill this board for me. Write an algorithm to do it or do something. It's not a trivial question. It's not this kind of questions like, what was the other one here? This is odd. Of course it's odd. If this is odd, 2 times that is going to be odd, right? That's it. Easy. This is not that kind. It's not that obviously easy. So how do we do it with induction? Of course, there'll be an induction step. What's going to be the induction step? If it works for board of size 2 to the k with any block spot, then it works for board with size 2 to the k plus 1 and any block spot. Be careful with this block spot. The blocked spot, I'm going to assume it works for any board with any block spot, and prove it works for every board with any block spot. There's some version of this problem that assumes the block spot is in a corner. But we say any block spot. So how can I relate? Now, that's my induction step. How do I relate the k plus 1 with 2 to the k on such a board? So when I move from 4 to 8, right? Because this is being 2 to the k. If my current board has 8, right, so let's make a plan here. If k plus 1 board has what relation to the K board? How do I relate my new customer to K plus 1 board with the previous customer? So I have this board, and it's 2 to the K plus 1 times 2 to the K plus 1. And before I even start, I have to find that relationship that controls the induction step. How do I even get to a 2 to the K board, the previous board? I'm not even worried about the L shapes yet. I just have to figure out what's the mechanism to move from the K to K plus 1. That works differently for boards than for lines, than for sum, than for products. How does it work?
So the K plus 1 board is 4 and 2 K boards.
Right. If I split half and half. Is that true? If I split it half and half, is every board 2 to the K, 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 2 to the K? Is that true? Hands up who's with me. Now I worry about the actual shapes. Where is the damn block thing? Right? Well, I don't know. I have no control over that. Maybe it's in here. Maybe not. Could be anywhere. But let's assume it's somewhere. Can I know for sure it's in one of the boards? Right, because it's gonna split. All the squares will go right in here. The split is like in the middle, right? That's the split. Clearly, every little square goes in one of the quadrants. Whoever got that quadrant is done. Okay, so now this board is really looking like my friend here, right? Like, aha, what did I found here? This is a previous board with a block thing in it, right? Well, then I know how to do this. Smiling faces, right? I've just split my board into 4, and one of them, it's a 2 to the K by 2 to the K board, and has a block in it. Isn't that exactly my previous case, my previous K? That looks good. What about the other 3? They have 2 to the K size. That's good, right? It's exactly the previous size. What they don't have is what? They don't have a block in them. So I can't fill them. I can't use the induction hypothesis because the induction hypothesis works if you have a block. Right? You got to be very exact about this. This one, can I fill this one directly? Say, okay, it's a 2 to the K board with 1 square block in it. I know how to do it from the induction hypothesis. Hands up with me. But why can't I do this again? If they have the size to the K? They don't have the block. So this is what I need, a creative idea.
Well, so we know that the board can always be filled, assuming that you fill in randomly one block.
Any block.
And
If
we
you have a
3
block.
boards, which means that there are, if we were to fill them up, there would be 1 empty square in each of them, and that could, we could put another L shape.
Right, so it doesn't quite exactly work like that. It doesn't say you can fill the board up to the remaining block, although it's the same thing. What it says, if you fix the block, if you block something, if somebody blocks something, you can fill that board. That's what it says, right? It doesn't say you can fill a block with a full board. What it says is, if you block something here, you can fill it.
Yes, so we-
Yes.
You can block the top right block of the bottom left square.
Where? Bottom left here?
Yeah, that block, and then top
Block
left,
this one, and
then top left, the bottom right.
this
So,
one?
Yeah.
Yeah.
And then bottom left, the top right.
Block those 3 specifically, 3 blocks. Can I use the induction hypothesis now for these 3 boards? Do they have 2 to the K, and they have a block in them? It has to work for any block, so I can put the blocks whatever I want. Now, why did you put the blocks here?
Because it forms a shape.
Because at the end, I can add an L and fill it up. Everybody follow him in here? If I block this particular 3 square, I get this done, and then I'm like, okay, I know how to fill this one too. I just put another L in there. Okay? So all these problems are structural problems. The technique for moving to k plus 1 clearly depends on the structure of that thing. So squares, that, lines with intersections and regions, so on and so forth, right? So in here, the step is difficult, requires blocking 3 particular boards of size 2k such that one extra L fills these blocks. And that's back to his question in the back, what structural induction? The whole mechanism here depends on how exactly these blocks play out.
So in this case, like, this is also weak induction, right? So
Yes.
Structural induction doesn't say, oh, strong.
It's from k to k plus 1. The statement is it can be fill a board with 2 to the k by 2 to the k sides with any missing block. So the next one is 2 to the k plus 1. All right? Okay. So I think we've done quite a few induction problems. Let me give you one as an exercise, a famous theorem by Euler. Yes?
Wait, sorry, one question. Before you go forward, so the base case for that one will be your k equals 1, and you cut
So
out
base
the
case, k equal 1, it's a 2 by 2, right? It's 2 to the 1. So now whatever block is missing here, I can put an L to fill up the rest. So he's right. If this block is missing, I fill this L. If this other block is missing, I put this L, so on. Yes.
Wait, so when I'm writing an induction proof, you want to specify, I know you did this before, where that k starts, like exactly.
Yes, when you prove the induction step, you should say, I'm going to k plus 1 for any k starting at 1. So 1 to 2, 2 to 3, 3 to 4, 4 to 5. Then for the base case, it's going to be k equal 1, because that's not proven via the induction hypothesis. Here's a cute geometric problem. It says that in any convex polyhedra, let's say 3D, and I have the same questions as I always do, what if it's 4D or 5D, how is this going to play? But let's say 3D. The number of edges plus 2 is the number of vertices plus the number of faces. So let me show you an example. I'm going to leave it as an exercise. If I draw something that looks more or less like a cube. Right? How much is the number of vertices? This is an example. I'm not proving a problem. Just taking an example. I want to see what this even means, right? Like, what is this? How many vertices are in this cube? How many faces? Faces means sides. 6. How many edges?
12.
Does it work? It's 12 plus 2a plus 6. All right. Let me go a little further as a hint, because we already said it's induction. Here's the new vertex. Call it V9. Suppose this guy sits on top and it adds, it adds a bunch of edges and faces and whatever else he does, right? Let's assume this guy, it's gonna modify my polyhedra a little bit. It's gonna be like, okay, I have edges here, and now this whole top becomes an addition. It's like a house, you're putting another room. What is the delta? What's the new V now?
9.
And what's the delta? How this change? Plus 1, right? I added 1 vertex. How about the faces? How many faces are here now?
9.
How many I have before? 6. I added how many triangles here? 4, but did I get rid of one, the top face? So there are how many?
9.
What's the delta? And how many edges did I add?
4.
Did I get rid of any previous edges?
Yeah.
So how many edges are here?
16.
Extra. No, sorry, 16. So that's plus 4. For this to still be within the same constant, it means the deltas of V plus F has to be the delta of edges, right? To be still exactly this. Now, that's just an illustration. Doesn't mean it's a full proof. But the question is, why is this true for all polygons? It's a famous theorem by a famous mathematician. Yes?
Could you look at it in a similar way in terms of not adding a vertex, but instead cutting a plane through a corner and seeing how that would affect the new shape?
Sure. So I have a corner, what he's saying, I'm looking at this cube. I cut it. Now instead of one vertex, I end up with, 3 vertices. I get a triangle in there, right? What he's proposing is, if I'm to chop off this corner with a saw, I'm getting a little bit of a triangle here, right? Instead of the actual corner. So I'm having 3 vertices. I'm adding a face, right? So on and so forth. So he's proposing some different induction mechanism. Yeah. As an exercise, I think this makes sense to think about. Here's another problem that I want to bring up. Is the one that I mentioned last time. I just mentioned the problem related to your honors problem was the height of a binary, not search. Any binary tree doesn't have to be a search tree with n nodes. So the height of the tree is the number of levels. This is level 0, and then that's level 1. These guys are on level 2 here, level 3. That's the height. It's how many edges you have to go until you go all the way down. So the height is the maximum length of a path. This is level 4, level 5. So this D, we need to prove that D is at least log base 2 of n with the fluorine. So if you have n nodes, the intuition is to minimize this depth. You have to fill up the tree. You don't want to go down too quickly unless the tree is full. And then you can easily see in that tree, right, a full tree is something that goes. It doesn't go to the next layer until it fills all the previous layers, right? So it will fill everything here. It's not allowed to go down unless it completely fills the new layer. And if that's the way to minimize the depth, which it is, it's easy to see why this property is true. The maximum number of nodes that fit in a certain depth is something. But that's not the way I want to go by this proof. I want to go by induction. And what I'm going to do is, I don't want to specify weak or strong induction first because I'm not sure. What I want to say is, here's I have a binary search tree, binary tree for n nodes. Here's the root, and here is the left subtree, and here is the right subtree. And let's just say this is one node, this is p nodes here, and this is q nodes. Obviously, n has to be 1 plus p plus q. So if I have n nodes and I make a tree out of them, any tree, there's going to be a root, and there's left side and right side. In binary search, we have the additional property, binary search trees, that the left side values are smaller than this guy, and this guy is smaller than this values. So now, if I do induction, where is this P of n is going to come out? Who's going to imply the property at n? This property. This is my P of n right here. It's going to come out of who? For what values? Is it going to be P of n minus 1? When I prove this property to come out this, and I'm going to get it out of the previous n?
P and Q.
Right. I'm going to use this property for the subtrees. These are binary trees on themselves, right? Because any binary tree, if you cut just a piece of it, it's still a binary tree. So I'm going to use the induction for P and Q, and then it's going to imply n. But can I declare in advance who P and Q are? Like, these other problems where Sk depends on Sk minus 1 and Sk minus 2. Can I know in advance who P and Q are before I see the tree? Do I know how big is the left subtree? Or the right subtree? I don't know who P and Q are until I see the actual tree. So what kind of induction is this? This is definitely a strong induction. And because I don't know where P and Q are, who do I actually need to put here? Again, where does P and Q can range from? What's the maximum they can be on one side? N minus 1. What's the minimum they can be? All right. If the whole tree is on the right side, it's root plus the right side. Okay. So I don't know who P and Q are, so what am I going to put here? I'm just going to put all of them. P of 1, P of 2, up to P of n minus 1. Thinking, these guys P and Q will fit somewhere in here. And I just noticed that 0 might be there, and 0 is not in my thing. Can I add 0 in this equation here? Say d is bigger than log base 2 of 0? Can I? No, I cannot. Log of 0 doesn't work. So let's say this is for starting at 1. I have to deal with this 0 case separately. If my tree really breaks as a root and all the other n minus 1 nodes, so I'll have a special case. P equals 0. Because it's not part of my induction hypothesis, P equals 0. So if that happens, if my tree really breaks 0 versus n minus 1, then I'll have to deal with that. So now, how my proof is going to go here? The depth that I'm looking for, let's call this dn. What's the relationship between this whole thing is dn, and this thing here is dp, and this thing here is dq? What's the relationship between the new customer, depth of a tree for n nodes, versus the previous customers? There's a p nodes tree here with a depth, I don't know what depth, and there's a q nodes binary tree here with a depth. What's the exact relationship between the new customer and the old customer?
The new one is 1 greater than the maximum of the depth of P or Q.
Like that?
Yeah.
The new depth is 1 plus whichever was the maximum between those two, right? We can assume here, let's say, let's assume B is at least as much as Q. This is not a losing or restricting generality assumption. One of them has to be bigger. If P is smaller, I'm going to swap the tree and get P bigger, right? So P bigger than Q, that means P has to be at least n by 2 minus 1, right? N minus 1 by 2. Because one node is the root, the other two are n minus 1 nodes, the trees together. P plus Q have to sum up to n minus 1. P is bigger, so it has to be at least half. That means P has to be at least the ceiling of that, right? It's either that as an integer, but if P is an integer, right? If it's at least 32.5, it's got to be 33. So then I'm going to say in here this is bigger than. I use the fact that P is bigger, but in here I say 1 plus P. What I mean is the maximum between those two is going to be greater than or equal with either one of them. And I use the tree that has at least half of the nodes. So instead of maximum, I'm saying which tree has more nodes here. Don't be confused. The tree with more nodes can have a smaller depth, because a tree could have few nodes but deep versus another tree that has it's all balanced, and has a smaller depth but more nodes. Nevertheless, I only need the one that have at least half of the remaining nodes. So now, by the induction hypothesis, this is greater than 1 plus log base 2 of P which one, I'm going to write log of 1 as, can I put the 1 inside the flooring? If I add an integer from outside to inside, can I do that inside the flooring and ceiling?
Yeah.
Right. So let's do that. 1 plus log base 2 of P. And now 1 is log base 2 of how much? 2, right? Which is log base 2 of 2P. Follow me? I proved this all. 1 inside the floor. 1 is log base 2 of 2. But now I have the sum of 2 logs. That's 2P. Now, this is what I am. And what I want is, I want to show that, I'm going to write it here. I want what? I have to get that this is log base 2 of n. Log base 2 of 2p is at least log base 2 of n. I'm going to put want. Every time I write wishful thinking, not stuff that I know, but I want to be true, I put a want sign. And leave it as an exercise. With a hint, and even and odd 2 cases. Okay? So prove that this is that would be equal, but I think you have to take 2 cases, n odd and n even, to make it an exact. So now this induction step proved that the property was true for anything less than n, any p and q less than n. It's going to be true for n if you make it work with this exercise at the very end. And then, of course, I need a base case, like when n equal 1 and 2, what's the maximum, minimum height that you can get. So that proves that the height of a tree has to be at least log n. The reason why I show you binary search trees is that on average, if you do the trees that we discussed, left values go on the, smaller values on the left, bigger values go on the right. Those trees, on average, are exactly log n. So their average is the minimum, which makes them very good for search, right? Everybody can see a search in here can take a long time because I keep going down and down and down. But if the tree is balanced or the height is about log n, then every search will take logarithmic number of steps to find the value. So there is another proof that we don't have here that says on average, if you have a random sequence of numbers and you make a binary search tree out of them, the average depth of the tree is logarithmic. That's a complicated proof. If we have time, we're going to do it before the term ends. That's fundamental why binary search trees are good. But for now, let's do the simple one, which is the depth of any n numbers in a tree, whether it's a binary search tree property or not, has to be at least log n. You can't get faster than that. So I want to show you something about the harmonic series, because we did it in the past and we don't want to leave it like that, like the regular section did it, and leave it, like that. Which is, it's a little bit over what you need for the homework. But let's see how far we get with that. So this in here, this next 20 minutes or so is advanced material. Fair warning, this is not going to happen in the homework at all. It's going to happen if you do a master in math. So I wanna give you a 20 minutes brief into why the harmonic series behaves the way it does. Everybody have seen so far the fact that Hn is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over n is about the natural logarithm ln of n. ln means log base e. We've seen this approximation before, right? The harmonic series is about logarithm. And it's actually very, very close to the logarithm. So it's a good approximation, not to say asymptotically, clearly this goes to infinity if it's like logarithm, because logarithm goes to infinity. But why is that? Here's why. First of all, the biggest difficulty with this is that we don't know who E is. That's the biggest problem right there. Who is this E? Not approximately, but who exactly is E? So I'm going to put a bunch of results on the board and we see how far we get with the proofs. The first result is that this A of n equals 1 plus 1 to the n at n, it's a sequence that is monotonically increasing. And Bn, which is 1 plus 1 over n at n plus 1, is monotonically decreasing. To be specific, we have the following: 1 over n at n. It's smaller than 1 at n over n, n plus 1 at n plus 1. This is saying when you increase n, you get a higher value. That's what this is saying. It's increasing, so increasing means if instead of n equal 5, I put 6, I get a bigger value all the time. What this one's saying is that 1 over 1 at n plus 1 here at n plus 2, it's, so what happens if for this other series decreasing is that if I move from the next Bn to the Bn plus 1, so let's write it this way. This is An, this is An plus 1. An plus 1 is greater than An. This is Bn, this is Bn plus 1. What this is saying, B's are always going down and A's are always going up. I'm going to say this in here, it's also bigger than that. Is that true? Right on it easy. Is this obviously bigger than that? It has the same base, 1 over 1 at n plus 1, 1 over 1 at n plus 1. And it has a higher exponent. Right? It's n plus 1 versus n plus 2. Now, is base bigger than 1? If a base is bigger than 1, higher exponents means bigger values, right? Hands up, who's with me? So that's easy. I'm also going to say those two converge to same value. I mean, there can be a gap. What we're showing here is that this series is increasing, and this series here is decreasing, right? These guys, all of them, are bigger than all these guys, because we always have this inequality. And what I'm saying is, there is no gap left in between. These guys coming from below to some magic level. All of these guys are below the magic value, and all these guys are above the magic value. And these guys coming little by little down, and these guys coming little by little up. I think at the very end there will be no gap left between the two limits. If this guy converges to some limit, this has to converge to the same limit. There's no way to have a gap in between them. So the gap will look like these A's are going slowly to some limit, and these B's are going slowly to some other limit, and there is a gap in between. But I'm saying in this case, there is no gap. If this is finite, bounded to some upper bound, and this is lower bounded, the bound has to be the same. And guess who that magic bound is, where both of them going up? E. That's E. E is the limit of AN and the limit of BN. Because this was monotonically decreasing, that's monotonically increasing, and they have no gap in between. And since one's going up, the other goes down, at some point they have to converge to something. Because monotonic sequences have to converge. Okay? That's part number one. That's the hard part. If we prove this, the rest is easy. So let me do the rest first, and then come back to this end. So assuming I know that stuff, how do I get from there the harmonic series and all its properties? Here's what I'm going to say. The immediate consequence is that 1 over n plus 1 is smaller than natural logarithm of 1 plus 1 over n, which is smaller than 1 over n. That's coming from that. It's very easy to show. Let's make a quick proof here. These inequalities here, I have to raise at the power let me write this in a different way. And so what I do here, this inequality, I think it's exactly this one. It's the same inequality. So what happened from here to here, I move the n on this side of the logarithm. You guys see that? This whole thing, it's exactly this one here. How about in here? I move the n plus 1, so this part, including the 1. This is this inequality here. But seeing it with the n plus 1 on the side of ln of 1 over n, right? Everybody sees that? So this right side is the same as the left side if I multiply with n plus 1. 1 smaller than this. And this one, if I multiply with n, I get 1 bigger than that. So I don't put any signs between those equations because they're equivalent to each other. But you have to see where they're coming from. This one is this one here, multiply with n plus 1. This one, multiply with the n. Now, n goes inside the logarithm. How much do I get? ln of 1 plus 1 over n at power n, right? Because the n can go inside the logarithm as an exponent. Smaller than 1, smaller than logarithm of 1 plus 1 over n at n plus 1. Now if I transform this into exponential, I do e at that power. How much is e at this power? This is the natural logarithm of something. If I raise e at this power, what do I get? I get the inside the log, right? 1 over n at n. Well, how much is e at 1? E, which is smaller than, how much is e at this? 1 plus 1 over n at n plus 1. Isn't that exactly that? This is the left, this is my an, this is my bn, and I just say this bn was going down, this an was going up, and both of them have the limit e. So e sits between all ans and all bn's. So now I read this backward. This is from that theorem because the limit e is here in the middle. The limit. So e bigger than a's, smaller than b's. Do those steps, take the logarithms, manipulate inequalities, and I get this part in here, which I can rewrite as 1 over n plus 1 is smaller than, this is a fraction. This is n plus 1 divided by n. So how much is the logarithm of a fraction? N plus 1 divided by n, smaller than 1 over n. So I'm writing it again as a difference. 1 over n plus 1 is smaller than ln of n plus 1 minus ln of n. Smaller than 1 over n, right? Who's up? Who's following me here? All right. Who wants to follow and follows me here? Maybe some people, went to sleep. So I start with that. That's pure magic, right? And then I say from there I can get here if I read it. This is the the theorem I had, and I read it this way. I get here. This is a very easy manipulation. N plus 1 by n is a difference. Now I'm going to telescope this. I'm going to say, what happens if I sum up for all n's for some values, say 1 to some big N of this. 1 over these summations here is going to be the sum over ln of n plus 1 minus ln of n from n equal 1 to a big N. This is the sum of all n's from 1 to the big N of 1 over n. So I'm writing these inequalities for n equal 1, 2, 3, 4, 5, up to a million, and I'm summing them up, which I can, right? The left side is more than the middle side, more than the bigger side. Now this in here is the harmonic for n plus 1. The logs telescope with each other, right? This is natural logarithm of 2 minus natural logarithm of 1 plus natural logarithm of 3 minus natural logarithm of 2. The last one is n plus 1 minus logarithm of n. You can see the telescoping. 2 with 2, 3 with 3, so on and so forth. So this is the harmonic number for n. So now I've got harmonic of n plus 1 is smaller than, who's left here? How much is this is logarithm of n plus 1? Big N. Because I sum up to the big N. Logarithm of n plus 1 is right here. How much is log of 1? 0, so I don't have to write that one, smaller than harmonic of n. So clearly this shows that the harmonic is super tight with the lobes. Because the harmonic would be bigger than the natural logarithm of n, right? Same exact inequality. So every harmonic is between logarithm of n and logarithm of n plus 1. Now the two logarithms of consecutive numbers are getting asymptotically, the difference between this and this is asymptotically tied to 0. So that means the hn has to be extremely close to the logarithm of n. Yes?
Is it also true that harmonic of n plus 1 is harmonic of n minus 1, and so it's also tight that way?
Yeah, I think so. The point is, logarithm being the difference, the deltas between logarithms going to 0, it means the difference from here to here goes to 0. Hn is trapped between two logarithms. It has to be asymptotically tight. From here, we can prove all the inequalities, and they have the extra benefit of defining E. The calculus version of these theorems use the E already defined to use integrals, which is all good, except you need to define E first. This version is much more math clean because it provides a very clean, discrete definition of E. Now, what do we have? 4 minutes? How about this in here? Who can do that? Right? I'm going to start the proof, and you guys finish it, and I'm going to give you a hint. Let's do this one first, because this is easy, and that is the same as this. So I want to prove that 1 plus 1 over n at n is smaller than 1 plus 1 over n plus 1 at n plus 1. Well, let's see. 1 plus the sum for k for 1 to n factorial. Remember? Is that true? Am I doing it right? I'm doing the binomial expansion for x plus y to the n. Right? X plus y to the n is the sum of k for 0 to n, n choose k, of x to the k, y to the n minus k. I'm going to try to prove it without this. I'm saying that's a bonus. Clearly a positive value. If I manage to prove this is smaller than that, without that extra value, it's even better. So clearly adding that to it will help. I'm going to remove that. And then 1, of course, goes away with the 1 here. And I'm going to say sum from, I'm going to move everything into one sum. N factorial, k factorial, n minus k plus 1 factorial. And see what's left in there. N minus k plus 1 divided by n to the k. Minus n plus 1 divided by n plus 1 to the k. This, I want to prove is smaller than 0. I say equal because these bonus will help me just in case they're equal. So what happened here, I moved the right side into the left side, and I did everything I could common factors, the n factorial, right? So where this n plus 1 factorial went? There is an n factorial in the front times the n plus 1 here, and I wrote this sum as a one sum of the common factors times this. And now I'm going to say wishful thinking. Wouldn't be nice, I have a sum here, if all the terms are positive, sorry, negative. Because if all of them are negative, clearly the sum will be negative, but not necessarily the other way. So So I'm saying, would it be nice for this guy to be negative? N plus k and minus k. Plus 1 divided by nk to be smaller than n plus 1 divided by n plus 1 to the k. Because if that's true, if this is negative, I'm done, right? It's a sum of terms, all of them negative. So that's your exercise. If we prove this, did we agree that we prove the whole thing? If all these terms are negative, the sum is negative, this is smaller than that, we prove this inequality. This one is the same exact proof, and then everything follows, including y harmonic, is related to the logarithm. So let's prove this by Friday.
He doesn't need to visualize the square. You're asking us to visualize when it has no vision. What does that even mean? Well, that's the point. My idea is that you visualize all you have. All right, you know what? I came up with your mind, or is the images you derive in your mind completely dependent on what you see? How can you? Blind people do not have any. People who have been blind their entire life do not have any. So they can't have it. Not ever have like red in their thing.